Electricity, Section 6. Yay, pow! Right into more components that you need to know the purpose and function of. Of course, inverters have been mentioned before. Why do we have them on the aircraft? Because we have to run AC components, and every now and then, all we have on the airplane is DC power. Say, for instance, we haven't started the engines, we don't have the APU running, and all we have is our 28 volt, 25.2 volt DC battery. If we hook this up to, say, a 28 volt DC bus, we could run an inverter off of it, and we could then connect that to 28 volt AC bus, and we could run things off of that AC bus even though we didn't have any alternating current generators running. That is, before the engines get going, all we've got, including the APU, all we have is the DC battery. So an inverter changes an inverter changes DC. Hey, wait, here's the function. How does it perform its purpose? By changing direct current and turning it into AC. And typically what will run off of there are engine gauges and some avionics, but that's on another slide. And there's no particular symbol that you have to know. It varies quite a bit widely based on manufacturer. Here's a picture of an inverter, and you probably can't see it in this video, but it says input 26 volts DC and output is 400 hertz. Wow, cool. Rectifier does the exact opposite. Its purpose, or why it's on the aircraft, is so you can run DC components even though your primary power source is alternating current. How does it do it? It just changes AC to DC instead of DC to AC. You probably remember, or don't remember, an DC alternator. We're getting alternating current in the output windings, and we pump it into the diodes. Effectively, these diodes right here are a rectifier. Let's see if yep, a rectifier, because you're putting in AC and you're getting out DC. And here's an example. Let's say that you have you've got a 28 volt DC bus, and you've got a battery on it, and over here you have a 28 volt AC bus, and this is getting fed off of a step down transformer, which we'll get to that, off of the main 110 208 volt AC bus, and this could be a step down transformer, and it could be fed by 110 volts. We reduce the voltage down to 28 volts, and then we have a rectifier that gets fed off of alternating current, turns into DC. Now we can charge the battery, so we can have our big ol' honkin' AC generator that runs the main bus bar. We can step it down, and now we can have lower voltage alternating current if we need it, and we can also now change that low voltage alternating current with the rectifier into low voltage DC and run that. And in fact, what you're going to find is that you can actually bypass this step completely and have a step down transformer and a rectifier in one box, which is on another slide here. You could have a step down transformer and a rectifier in one box and run it straight off of this bus bar into the transformer rectifier and power the bus. So you might have a rectifier all by itself. It's also very common to have a step down transformer and a rectifier in the same bus, in the same box, so you can run this high voltage alternating current and turn it into low voltage direct current. Transformers, sometimes they're robots in disguise, but in this case they're not. The electrical symbol for a transformer is two coils facing each other, and usually, although not always, they draw an iron core in the middle. Of course, this is soft iron, doesn't have any retentivity. The purpose, or why do we have transformers on board aircraft? It allows you to put different voltage components on the same airplane. You can have stuff that runs off of 110 volts AC, you can run stuff that runs off of 28 volts AC, and we can use this to step down the voltage. You don't have to draw this typically it's not drawn this way, but let's say that this right here, let's say we have 100 windings, and on this side we have 25 windings. If we input on this side 110 volts AC, since the ratio is 4 to 1 on the windings, it'll reduce the voltage by a factor of 4. So 110 divided by 4 is a little over 25. So 27.5, 27.5 I think is what it is. So wow, that's really close to 28. So a step-down transformer in an aircraft that's producing already 110 volts alternating current, we could have a 4 to 1 step-down transformer, and all of a sudden we'd have 27.5 volts AC. And of course, we're pilots, we're going to round to the nearest whole number, 28 volts AC. And so now we can put different components that run off of different voltages, but still, we only have to have one type of a generator on the aircraft, and its function, of course, is to step up or step down. And the vast majority of transformers on airplanes that you're going to find are going to be step down. Now you're going to find that they're only found in AC systems, and the reason is that they work off of electromagnetic induction. And you're going, what? Electromagnetic induction? I thought that was only for generators and alternators. Well, if you had that thought, I'm glad you're thinking. But you can have electromagnetic induction other ways. Let's say we run electricity through this coil. It's going to generate lines of flux. And as they're forming, they're going to start from the center of the wire and move outward. So these lines of flux will actually cross these other wires. Wow, lines of flux crossing wires induces a voltage. And if there's a complete circuit, we'll also get amperage. And so if we have more wires over here crossing fewer wires over there, we'll get a lower voltage. You could also put the volts into this side and get a higher voltage on the other side, so that would be a step-up transformer. Then when these lines of flux collapse, because remember this is alternating current, and so we've got a nice sine wave going on, so the number of amps versus time, the amps are going up. As the amps are going up, the lines of flux are expanding. Then as the amps go down, these lines of flux will collapse. So we have movement across the wire, movement back across the wire. Then we have electrons going in the opposite direction, but they're getting more of them. Remember, this distance here is just quantity. So lines of flux cross the wire, but they're opposite polarity, so it causes current flow in the opposite direction. So the only way we can keep these lines of flux continually expanding and collapsing and expanding and collapsing, so we have crossing of these wires, so we have electromagnetic induction, is to continually vary the amps. And in an alternating current circuit, we continually vary the amps. If we have a DC circuit, that first thousandth of a second, the lines of flux will increase as the amps do, but after that, it's constant. And if we have constant amps over time, these lines of flux would expand to their maximum, and then they would just sit there. So we'd induce current flow for that 1,000th of a second as the amps were increasing and as the lines of flux were crossing. But then after that, constant amps, the lines of flux won't move, no movement, no electromagnetic induction. So we need alternating current to have a transformer do any good. 26 volts alternating current bus. Now you're going, 26? What's up between 26 and 28? Nothing. It's just like the difference between a 14 and a 12 volt system is that it just depends on who labeled it. 26 volts AC, 28 volts AC, same thing. As far as pilots are concerned, we're going to say that this is essentially a constant voltage. So whether or not it's 26 to 28, we're going to say it's the same thing. Why do we have this type of a bus bar on the aircraft? Typically avionics and engine gauges are going to be powered off of this 26 volt AC. So we can have engine gauges, and it's also very common to run avionics off of a 26 volts AC system. And guess what? We could take a battery while we're on the ground. Whoops, can't even draw a battery today. We could take a battery and run it through an inverter, and so now we could use the engine gauges for engine start, even though there's no engine running and spinning an alternating current generator, and we could get ATIS and get a clearance and use the avionics while we're on the ground with just the battery, running it through an inverter. So it's very convenient to, and we didn't have to step up the voltage. You know, this is a 25.2 volt battery. Even if this was 25.2, our engine gauges will work fine, and so will our avionics, because we're going to even say that between 25.2 and 28, we're going to say that that's a relatively constant voltage as far as electrical systems on airplanes is concerned. TR or TRU is two different abbreviations for essentially the same thing, a transformer rectifier unit. Don't worry about drawing a symbol. I typically draw it with a T and an R on it to tell me that there's a transformer, or step-down transformer in it, and a rectifier. So we're going to feed it with high voltage AC, and typically that's going to be that 110 volts AC, and what we're going to get out of it is low voltage DC, 28 volts DC. And so we need a step-down transformer. While it's still alternating current, we're going to reduce the voltage by using a step-down transformer and get the alternating current into direct current. So the transformer will change it from 110 volts AC to 28 volts AC, and then we'll feed it through the rectifier, and that'll change it from the alternating current into the direct current. So why do we have them on board? I showed you in that last slide. It allows us to have low voltage DC components. For instance, on a 777, didn't mean to go that far. On a Boeing 777, it uses transformer rectifiers to power the pilot displays in the cockpit. The pilot displays in the cockpit run off of 28 volts DC. So what we need is a 28 volt DC bus to feed these things, and which works out fine. On the ground we can use battery and we don't need an inverter, but in flight we don't want to have to run it off of the battery all the time. All we really want to do with the battery is charge it and let it sit there and wait for an emergency. So what we can use is a step down transformer and then rectify it, so we can have that nice big 110 208 volt AC bus, and we can have a transformer rectifier feed our 28 volt DC bus. And of course you're probably, I'm sure, you're going to put more than one transformer rectifier into the system, so that in case one quits, you're still going to have another one. So on a 777, there's actually more than two transformer rectifiers, so in case you have a failure, you have plenty of them left over. So that way you can have low voltage DC, we're talking about 28 volts DC, and run those components. That's the why. And how does it do it? Reduces the voltage and then changes the AC to DC. Bus Tie Contactor AK.A, also known as a relay. Bus Tie Contactor and a relay are identical. They're the same thing, they're just two different names, except when you start flying big airplanes, they typically call them contactors. So a contactor and a relay is the same thing. If we use it to tie buses together, it's the same thing. In transport category jets, big biz jets, big turboprops, big turbine-powered helicopters, there's going to be bus bars all over the place, 110 208 volt AC, and we're going to need to, at some point, connect that to another voltage. Let's say that this is the essential AC bus, and this is a bus for the lavatory and a galley, and so we can run things off of it. But if we wanted to disconnect it, it'd be really easy, because we could just run a little wire with a switch to the cockpit. But this would be called the bus, that switch would be labeled Bus Tie Contactor, essentially because it's connecting two bus bars. But now we're using a relay. So when you start talking big airplanes, we're going to have contactors. Dun, dun, dun. So interestingly enough, if you look at the purpose and function of a bus tie contactor, it's exactly the same as a relay. Solenoid. just like the bus tie contactor, there's no symbol that you have to draw. With a solenoid, I'm not going to ask you to draw it, but a solenoid is very similar to a relay, except it's just a coil. It's just an electromagnet. But now what we're going to do is we're going to energize it, and so it'll pull something that's made out of iron, cobalt, and nickel closer to it. We can use this to change the position of a fuel valve. We can use this to disconnect the constant speed drive from the accessory section of the engine. You're going to find lots of solenoids. This is an isolation valve in a hydraulic system. Could use a coil to move a valve. So the purpose is to save weight, so we don't have to run lots of things all the way up to cockpit and then all the way back to wherever it is. And so again, we're going to remotely and electrically do it, but this time we're going to move something instead of electrically and remotely complete a circuit. Parallel bus versus split bus. Let's try parallel bus first. Let's say we got a bus, 120, 208. I think I was drawing 110 on the other ones, but it's really 120. 128 volts AC, 120, 208 volts AC, and we're going to connect them with a bus tie contactor, and we're going to run a generator, AC generator, on to this bus bar, and we're going to run an AC generator onto this bus bar. And we're going to say that most of the time we're going to leave this shut. We're going to leave this closed or connected or on. Now these two generators are feeding both bus bars simultaneously. The nice thing is if we're powering something off of here and powering something off of here, that if one generator goes down, since the bus bars are already connected, everything's still going to work. Now we'll end up turning off the things we don't need. We'll shed unnecessary electrical loads. So the advantage, and this is a parallel bus, because we're running the generators in parallel with each other. Essentially, as soon as we close this bus tie contactor, this is really just one bus bar, and we're running the generators in parallel. This side of the generator is connected to the bus, this side's connected to ground here, this side of the generator is connected to bus, this side's connected to ground. So they're parallel to each other. The advantage is that if one generator fails, everything on all the bus bars will keep working. The downside is we have to synchronize them. Remember XC and XL phase shifts? This generator has to be making the sine wave go up and down at exactly the same time as the sine wave from here, because we're feeding them into the same bus bars. So we have to keep them synchronized. If they get out of sync, we're going to have to adjust them. If you're a flight engineer on a 727, you actually get to do this manually and keep them synchronized. If they get out of sync, then XC and XL get all freaky, and now you got, the value of impedance goes way up and you're really unhappy. So the disadvantage of a parallel bus is that you have to keep the generator synchronized all the time. The advantage is that if one of the generators fails, everything on all the bus bars keeps working. Now, split bus. Split bus has become a lot more common, and a split bus is on a 777 and a lot of other airplanes. And there's a bus tie contactor. But in a split bus, this is normally open. And we're going to run an AC generator to power this 120 volt, 208 volt AC bus. And we're going to run a separate AC generator to run this 120 volt, 208 volt AC bus. And everything that's running off of this bus is only getting powered by this generator. Everything running off of this bus is only getting powered by this generator. The advantage of a split bus, this is split if this is normally open, the advantage of a split bus is that we don't have to keep the generator synchronized. This one can be going at 401 hertz, and this can be at 399 hertz, and the sine waves aren't synced up, and that's okay because they're not connected. Both generators are not feeding the same set of bus bars together anyway, so we don't have to synchronize them. That's the advantage. The disadvantage is if one generator fails, since it's not already hooked up, if this generator fails, everything on that bus bar is going to stop working. Now granted, if you got a computer in a 777, as soon as this generator fails, the computer is going to close this relay, for you and connect them together, and these things will start working again. But for that few seconds, excuse me, for that few seconds, maybe 5 or 10, these things are going to shut down, and they might be things you wish hadn't shut down. So the disadvantage to a split bus is that if one generator fails, everything on that one bus bar connected to that one generator is going to stop working until the bus tie contactor gets closed. The advantage is you never have to synchronize the generators, because once you do close this generator will feed both of the bus bars. Also, and whether it's a parallel bus or a split bus, if either one of the generators fails, you're going to have to shed unnecessary electrical loads. Shed is a specific aviation term that means turn things off. Shed unnecessary electrical loads, shed non-essentials, means turns off the things you don't need. Wow. Wild alternating current. Wild alternating current, or sometimes I've seen it called ACW, alternating current wild. It means that there's no frequency control. And if there's no frequency control, that means you don't need the CSD. And you're going, Mr. Johnson, if we don't have frequency control, then we're going to have XC and XL out the yin-yang, and that's going to be bad, and power factor is going to be less than 0.95, and those would all be correct statements. But you got to understand a few things. First of all, you're only going to find these things on turboprops, on big ol' honkin' turboprops. I've seen them, and you don't have to write this down, but I've seen them on the Saab 340, the de Havilland -8. I've seen them on, there was another plane. Oh yeah, the ATR 42 and 72. And in all cases, these are big ol' honkin' turboprops that primarily have AC systems, but they put an extra AC generator out on the propeller reduction gearbox, and they drive an AC generator, but then they only use it for heating purposes, to heat the engine inlet anti-ice, to heat the hot props, to heat some hot airfoils on the wings, to keep ice from sticking on it. So the heating elements, so it might look like this. We've got, say, an AC generator, and we've got resistors. Essentially, heating elements are just wires with the resistance, so the electrons will stop and give off their energy. And these heating elements don't care too much about whether or not the frequency is a little too high or the frequency is a little too low. The nice thing is, this is being driven off of the propeller reduction gearbox, so we got a propeller, and it's being driven by the engine, which I'm not going to draw in. Whoops, went too far. I'm not going to draw in the engine. But it's being run off of this propeller, and if you know anything about turboprops, typically they idle, say, at around 60 to 80%. And they typically run between 95 and 100% RPM. Now, these are RPMs. These are not power settings. These are RPMs. 60 to 80% would be idle in flight. Flight idle. So even though you pull the power lever back to 80%, it's still going to work pretty good, and you're hardly ever going to do pull the RPMs back. You just pull the power lever back, and the RPMs are going to stay at 95 to 100%, even at lower power settings. So the RPMs don't change very much. So the AC generator stays at a reasonable RPM. It definitely does vary. You do not get 400 hertz out of it. You might get like 380 to 420 hertz out of it. And here's, say, at 100% RPM, and here's, say, at like 70% RPM. But the components in there aren't going to freak out too badly, because resistors don't really care what the frequency is. That's the only time I've ever seen on an airplane where there was no frequency control, is on heating up engine inlet, propeller, and airfoil on some big ol' honkin' turboprops. Okay, you have an emergency. What are you going to do? Well, first thing is, I'm going to turn off stuff I don't need. Of course, you probably learned this flying a Cessna 172. If you have an electrical problem and you don't have enough power, you're going to try to conserve what you do have, so you turn stuff off you don't need. Of course, you're going to get power from any battery or batteries that you have, and this is true whether or not you're flying AC or DC systems. So this could be AC or DC. Same thing here. AC or DC systems. Even in an AC system, you can take that battery and have an inverter, convert it into alternating current, and a step-up transformer, and you could kick it up to high voltage. AC. You can reset the generator in a 172 or a Piper Seminole. You're just going to turn the generator switch on and off. You might have more than one generator or alternator. I've even seen piston-powered single-engine airplanes where they put a second alternator on it because they're going to fly IFR a lot, and nobody likes to fly through IFR and have the alternator quit and then only have the battery run for 15 minutes. So I've even seen some airplanes with two alternators on the same engine, and of course if you have one on each engine and you got more than one engine, then you got more than one alternator. So there's another good source of electrical power. If you're one of those transport category jets, large big business jets, big turboprops, or big turbine powered helicopters, then you're going to have an APU, an auxiliary power unit, on board the airplane or helicopter, and that's just another little jet engine that drives an AC generator. That's extremely common, and on a lot of aircraft you can fire those up in flight. Sometimes there's an altitude restriction. You can't operate them above a certain altitude, or you can't start them up unless you descend down to a certain altitude, but you can run those APUs in flight and get alternating current power. Here's a picture of the back end of a 737. That tailpipe, that's the exhaust for the APU, and here's a little jet engine, and it looks like an accessory gearbox, and somewhere in there is an AC generator. And of course, on a lot of these aircraft, you're going to find a rat, and of course in hydraulics, it's not uncommon to have a ram air turbine. That's what RAT stands for, ram air turbine, to run a hydraulic pump. But there's airplanes that also have rats that run electrical generators. Here's an example of a rat. Here's an example of a rat on an A300. I think it might have been an A330. And the rat on some airplanes, like the 777 and this A330 or A300, this air goes past it and it spins. So this is actually a turbine, even though it looks a lot like a propeller. Propellers are mounted in backwards, just so you know. Drives a hydraulic pump and an electrical generator. So, depending on what aircraft, you might have more than one or two or three different ways to get electrical power in case your primary method fails. Okay, since we're talking about alternating current, what kind of gauges can you monitor? We previously discussed a power meter, so you can tell whether or not the generator is operating efficiently. Of course, frequency is a big deal in alternating current. We like it to be at 400. You might want to have a voltmeter. You might have a voltmeter, depends on the aircraft. The constant speed drive, that hydraulic system might get too hot, so it's very common for there to be a constant speed drive temperature indicating system for the pilot. And of course, if it's hydraulics, it's nice to know if you're running out of hydraulic fluid in the CSD. The generator is going to get hot. It doesn't convert all of its energy from the engine into electrical energy. Some of it is converted into heat. So if something's wrong with it, it might get too hot. It's nice to know in advance. And of course, we've already talked about looking at or monitoring a nickel-cadmium battery temperature. So there's gauges that you would find in an AC powered aircraft. You know, they're all turbine powered, so you're going to have a NiCad battery. And yeah. So, what kind of controls might you have? Well, on-off switches, yay, especially if you need to turn things off to conserve your electrical power. Contactors, talked about that this time. Contactor, same thing as a relay. Master switch for the battery, electrical master switch. Tie and bus togethers. You can control your power system by connecting or disconnecting bus bars. Of course, we've already covered turning the alternator or generator field on or off as needed. Circuit breakers, if they're the kind that you can pull out, you can pull those out and use them essentially as a single pole, single throw switch. You can control things that way. And we talked about connecting the generator to the bus bar inside of the generator control unit, so you can connect or disconnect the generator from the bus bar. And of course, we talked about using a solenoid to mechanically or physically disconnect the CSD. Actually, this probably ought to read CSD connect, because you're really disconnecting the CSD from the accessory section if you hit that solenoid. So here's a diagram. You ought to find it, and let's label it. I'll use red. We'll start with where you can get power from. This one right here, that's the engine accessory section. So it's going to provide power into the CSD. And of course, right in there, I'm going to put a little S right there. S is for solenoid. And that's a solenoid that can retract the CSD gear into the CSD if you need to disconnect it. The CSD, we might have a temperature gauge, as previously discussed, and an oil quantity gauge. Actually, it would be quantity of hydraulic fluid. And of course, I would want to draw in the AC sine wave, so I would know that that was an AC generator. And of course, we might have a temperature gauge on that in the cockpit. So of course, now this box right here is a generator control unit. And the generator control unit, that's where the leads are going to get put in for the power and for a voltmeter. And my personal favorite, I'm just going to put a big capital F right there, for the frequency gauge. Now that's going to run into the 120 208 volt AC essential bus. Essentially, the essential there we go. The essential bus is going to have things on it that you really need. Like it might be, I'm going to say this right here, is going to be emergency cabin lights. That would be really nice to have no matter what. Fuel pumps. You know, maybe this is an electric motor. Fuel pump, maybe flaps. There's a lot of transport category jets, big biz jets, big turboprops that have electrically powered flaps, and if you're doing a short field landing, which in a jet, a 6,000 foot runway, that's a short field landing, you're really going to wish you had those flaps. I got diverted. I was going to do all the power sources. Here is our APU, our auxiliary power unit in the airplane. It's going to have an AC generator on it. And you're going, Mr. Johnson, how come we've got a CSD between the main engine and the AC generator, and here the APU goes straight into the AC generator? It's because APUs run at 100% RPM all the time. It's got its own governor, just like the governor on a constant speed propeller, that keeps it at 100% all the time. And so that's going to be geared especially to run that AC generator right smack at that one particular RPM, so it'll put out 400 hertz. So you don't need the constant speed drive with a governor in it, because we have a governor running the APU. But we're still going to need a generator control unit, and you can feed it into the essential bus if you want to. To start the APU, we're going to need an electric motor, and there's a contactor, and that's going to be connected to the low voltage DC, or 28 volts DC bus, and that can be powered through a contactor by the battery. So here we're going to have our NiCad battery, because this thing's only going to be on big biz jets, big turboprops. This complex of a system is only going to be on big biz jets, big turboprops, big turbine powered helicopters, and of course transport category jets. So if this is a NiCad, then this is going to be a temperature gauge. And so that could be a source of power. Also, if we want to run our engine gauges or our avionics on the ground, we could close this contactor as well as the contactor. Essentially, this contactor is run by the electrical master switch, or the battery master, that connects the positive side of the battery to this bus bar. If we close a contactor and allow power to go to an inverter, then we could run a 26 volt AC bus that could power the avionics and the engine gauges on the ground. And of course, we very likely have a voltmeter to tell us what's going on that 26 volt AC bus. And we're probably going to have a voltmeter on our 28 volt AC bus. Let's see. Hot battery bus. Look at this. Right coming off of the battery straight into here. It's hot all the time. There's no way to turn it off. Hot battery bus. And of course, on a transport category jet, big biz jet, big turboprop, big turbine powered helicopter, we might have things other than a Hobbs meter. On this Boeing 777, the APU fire protection system is on the hot battery bus, so even if we have full electrical failure, we can still use the fire protection system for the APU. And here, the inertial reference units. I know AS358 Advanced Avionics is not a prerequisite for this course, but the inertial reference units, you can only start them up on the ground. They need to be not moving. They need to be stationary when you fire them up so they can align themselves and be nice and accurate. You cannot realign them in civilian airplanes. You cannot realign them in flight. So you don't want to accidentally turn them off. So if for some reason you decided you needed to disconnect this contactor to turn the bus bar off, the battery would still be able to power the inertial reference units, and they wouldn't spin down, and then you'd be stuck without them for the rest of the flight. So that's very common. I think on the 777 they call it the ADIRU, Air Data Inertial Reference Unit. But regardless, the inertial navigation systems, sometimes they're called INSs, inertial navigation systems. So those would be common things to be on a hot battery bus. Okay. Here is a RAT, a ram air turbine. Now, on some airplanes, for instance, the Boeing 777, the RAT feeds a transformer rectifier, and it feeds the battery bus. Some RATs, 110 volt AC, straight into the essential bus. So varies by airplane. So let's see if we got the battery, the APU generator, the main generator off the engine, and the RAT. So there's all our power sources. If we've got this 128 volt AC bus, if we follow this right down here, this could be a transformer rectifier through a contactor, so that we can use the step-down transformer to reduce the high voltage to low voltage AC, and then use the rectifier to convert the low voltage AC into low voltage DC. So under normal conditions, we're going to power the 28 volt DC bus off of the essential bus, and of course now it is going to be a higher voltage than the battery, so it'll charge the battery, and of course it'll feed and power the hot battery bus, so the battery won't discharge. On the Boeing 777, like I told you before, some of the things run off of DC. So backup gauges is what we're going to write here. Backup gauges. That might be really nice to run it off the 28 volt DC bus, because we can power it off of the battery, and if the transformer, if the if the RAT's working, or the APU generator or the main generator on the engine are running, we can run it through transformer rectifiers and keep this bus powered. So that might be a good place to run backup gauges, and maybe that would be a really good place to have the cockpit lights. Because if anybody on the airplane needs to read magazines in flight, to read checklists in flight, it's going to be the flight crew on the flight deck. Okay, let's try this line right here. We can also power this 26 volt AC bus with an inverter. Boy, that was incorrect. Sorry. I hope you're not doing this in ink. We can do it with a step-down transformer. We can allow high voltage alternating current in, and through a contactor we can feed this low voltage AC bus, so it can get powered in flight without having to take power off of the DC bus. It varies a lot. You can rearrange this system quite a bit. But in this system, I've got a step-down transformer powering the 26 volt AC bus. Here we have a contactor, and that is going to run a non-essential bus. Non-essential 120 208 volt AC bus. And so we could run the lavatory, although some people would say that was pretty essential. And my example earlier was we could run the galley, run the coffee machine and the blender. Ooh, I don't know, blender probably ought to be on the essential bus, but you never know. Maybe the main cabin lights. Not the emergency cabin lights, but the regular main cabin lights. Maybe the exterior lights. If it's an emergency, you don't have to power all of these things. So if you need to shed unnecessary electrical loads, you could shed quite a few of them just by opening this bus tie contactor. and get rid of quite a few things right away. Here we have this system over here. This is the wild AC. So this is going to be the wild AC bus. And of course we have our uncontrolled AC generator. And of course we're going to have like propeller heat. And we could also have engine inlet heat. Engine inlet. Let's see if I can spell inlet heat. It's hard to draw really, really small with even a tablet mouse. And of course you'll notice that this system right here, the wild alternating current, you notice there's no way to switch on a bus tie contactor and get any of that power into the main system, or vice versa. Let's see. Oh wait, there's another place you can get power. You can get power from what we call external power. External power, that's this connector right here. And external power may be able to provide high voltage AC, and it may be able to provide low voltage DC. It depends on the ground power cart you hook up to it. I've seen ground power carts with 3-phase AC, including the ground, and then another 2 for 28 volts DC and 110, 208 volts AC. So it depends, but there are some carts that only provide 110 volt AC, 120 volts AC. I did it again, 120. But that's okay. If you feed the essential bus, you could, through a transformer rectifier, feed the 28 volt DC bus, and through an inverter run the 28 volt AC bus and run the engine gauges and the avionics for engine start. Heck, if the 28 volt DC bus is hot, you could charge the battery, and you could actually, since a hot battery bus is hot all the time, you could start up the inertial navigation systems by powering it off of the external power. Or if all you had was DC, you could run just DC into the 28 volt DC bus. You could run anything on the hot battery bus through a contactor and an inverter. You could run anything off the 26 volt AC, and yeah, sure, you could run the engine gauges and the avionics for engine start. Wow. So I think I got everything. So on the test, just pretend that I'm going to give you something that looks like this, and then pretty much you'll be able to point to anything on here and tell me what it is, label it, and then tell me the purpose and function as previously described on other slides. So what you might want to do is ask Mr. Johnson. He'll give you a blank one of these, and you could practice it. Probably what I'll do is, if you ask me, send me an email. I'll send you back. You can print this out at your leisure, and you can use it for practice. If you have any questions about this section, you know how to get a hold of me, and you know about the connections already. Thank you.